Hello, everybody. Welcome to another in our series of lightning talks about wildfires and wildfire management technology. As I've said before, my name is John Porton. I'm the Senior Research Manager at SciCore at the San Diego Supercomputer Center, and I am pleased to be joined today by Sara Brambilla. Sara received her PhD in chemical engineering from Politecnico di Milano in 2009, and she's worked for Los Alamos National Laboratory since 2010, where she currently leads the Countering Weapons of Mass Destruction team. In a little bit of a change, her work in wildland fire modeling has focused on fast-running micro-scale wind modeling in complex terrain, fire and atmosphere interaction, smoke transport and dispersion, and the impacts of smoke on road visibility. She's one of the developers of QUIC-Fire and QUIC-SMOKE, which we know are two of the models that lay underneath BurnPro 3D and are so important to its operation. And she's participated in the field campaigns to gather data for model validation. So she's been on the ground with these burn bosses we've been talking to. Very excited to welcome you, Sara. Thank you for joining us.
Thank you for having me. Let me share my screen.
I will get out of your way.
All right, in this presentation, I was planning on showing you how you could plan a prescribed burn using QUIC-Fire and QUIC-SMOKE and some background about them. And while I'm presenting here, of course, this is the work of a lot of people, and some are listed right here. So we'll go through what QUIC-Fire and QUIC-SMOKE, how they work together, and a little bit of the model description, and one type of application we've done for road visibility. So QUIC-Fire and QUIC-SMOKE, they start input-wise from fuels. And from that, we mean that we need 3D representation of your fuel. And that includes both surface fuel and canopy. And here in particular, we need to see if there is a separation between a surface and a canopy. As you can imagine, just a bed of pine needles, fire on those beds, it may never spread to a canopy if there isn't any ladder fuel. So the 3D description is very important to understand where the fire stays, where it spreads, and at what intensity. We also need ignitions, and we can accommodate dynamic ignition patterns. And by that, I mean that they can change in time, they can cover different areas. They can be like the standard head fires or beacon fires, but also more complicated street fires or spot fire, like from helicopter or drones. You can also do things like ring fires, which are usually used for cell replacements. Those are typical prescribed fire ignition patterns, and we're able to accommodate them. Weather-wise, we can ingest several types of inputs from spot forecasts, which are usually produced the day of the burn from someone from the local weather office with knowledge of the terrain where you're doing the burn. So this would be adjustment to what you can find online, specific to your area of interest. We can also ingest things like the FAA or RAS profile measurements or surface measurements. We can get 3D forecasts. Depending on your area you're covering with your simulation, you may need one or another product. We throw all of this into our QUIC-Fire model, which basically is this feedback loop between the fire and the atmosphere. That's the important part there. That's what we do that some other faster running models don't do. And so we can see how the fire, by moving into certain parts, creates updrafts, it creates energy, and that creates influence. And those winds change where the fire goes at the next time step. And so by having this loop, we can really predict how these complicated ignition patterns interact with each other. Once we compute where the fire goes and how much is emitted, for instance, in terms of a particulate matter 2.5, we hand this off to what we call QUIC-SMOKE. And the interesting thing here is this nested grid approach that we use, where we can represent the burn plot at very high resolution because there are a lot of spatial and temporal gradients. But then when you go to tens of kilometers away from the burn plot, you don't quite need the same resolution. All the gradients are smoothed out, so we can use a lower resolution. And that means just faster computational times. And this is pretty typical in meteorology, so we're leveraging this kind of ideas to carry the smoke away from the burn plot down to the downwind communities. What do you do with this? Well, you can do a number of things. One thing is fire effects. You can go look if you have reached your ecological objective with the burn. You can see if you reach your wildfire reduction potential with this burn, but you can also look at smoke effects, things like the population exposure, which is very important, and also visibility. And in particular, in this presentation, we'll focus on road visibility and what that means. So let's get into some of the more specific model description. So QUIC-Fire is based on this cellular automata model. And what that means is you have those energy packets coming out from a cell on fire where you have a current fire. And this energy can go into new fuels, this green tile, and can make it burn or dry up its moisture. It can also fall into an area with no fuel, which is this gray tile right here, and so be wasted in practice. Or it can be emitted into the atmosphere, and it generates the smoke you see rising from any fire. The way we describe the smoke, so if there was just one fire and no winds, you would see this column of smoke coming up, basically vertical, and you see it's growing in time, as you can observe from if you just look at a simple fire. But the important thing is when you have multiple fires, those smoke columns, they don't act as independent objects. They start interacting with each other. And it's this thing we call plume merging. Those plumes, those smoke plumes, they come together and they change the winds around the fire. And that's why prescribed fire behave the way they do. And the important thing is that when they come together, those cores, they intensify their energy. And what that means is that they basically shoot up. And that's why you see those vertical columns coming out fires. So those are important mechanisms to have in your model if you're trying to do prescribed fire. So in a nutshell, we're using complex ignition patterns. We have time and spatially varying winds. We can also consider topography, like in the animation down below. And because topography has a strong effect on where the fire goes, fire runs uphill. And also smoke attaches to the slope. So if you're thinking of smoke effects, knowing where your topography is very important. We do all these high resolution, usually horizontally 2-5 meters. That's why you're having a good definition of the initial field, not just something per hectare, is very important in our case. And we can run on a laptop. So you can run it on your own computer if you want to. So looking a little bit what it looks like once you throw all this into the model, well, you can see the top is all the inputs that come in. One is the fuel density, and as you can see, it's splotchy because it's not uniform. And we need all that description to really tell where the fire is going. The other thing is the fuel moisture. Again, if you have a more swampy area and more dry area, we want to see those differences. So that's where all the fuel description comes in and how it matters. And with that, we put ignition on top of all this, and then we let it run. And at the bottom, you see some example outputs. This is 5 minutes in. We see the fire started collapsing between the fire line. Those are the blue areas across the fire lines. And you start to have some production of PM 2.5, which is what gets into your lungs and causes issues. Right here is just an example. If you look at the picture at the bottom, those are prediction of from the smoke. Once you have emitted those PM 2.5, or we can also track CO, well, we'll go look where it goes. And so you can see right now the wind was going right to left, and that's why all those plumes are being dragged to the left of the screen. We can see the differences between also the other picture, bottom right. We can see the difference of this wind speed. When you have lower wind speeds, you have more vertical column of the smoke. If you have higher wind speed, the smoke is bent down toward the ground. This QUIC-SMOKE model is a Lagrange random walk model, and it considers, of course, turbulence, which spreads out your emissions. And for particulate, it also considers gravitational settling, meaning that the particles tend to fall out of the sky, basically. And we can take in all the varying in time and space winds and emission from QUIC-Fire. Those models were meant to be coupled together, and it has this nested domain capability I mentioned before. So let's see an application to road visibility. This in orange on the right of the top image, that's the burn plot. But as you can see, we're going out 35 kilometers just to see what happened on that highway. So these right here, in orange, that's a highway. So it's very important not to have smoke, and especially smoke that could reduce visibility. So the way we do it is we define a domain. We go out and we get the roads from OpenStreetMap. And based on the speed limit and reaction time, we define the braking distance. And based on that, we can say what's the minimum visibility you need so that you don't end up in the trunk of the car in front of you. So these are type of outputs we produce. In the top row shows how the plume is spreading in time. Those are longer distance, so it takes some time for the plume to diffuse out of the burn plot and reach the highway. And we can see how the minimum visibility changes with time. Those before the highway are more of country roads type, so maybe you're less interested. You don't quite care if their visibility is impaired. But as you go on the highway again, you want longer visibility needed to braking distance. The other thing, that's the bottom row, we can predict based on how long you exceed the braking distance limit, then we can calculate how long you will have to close the road. And that gives you an idea if it's just a temporary effect, just a 1 second effect, versus something longer, maybe a half-hour effect. And with that information, authorities can decide either to do the burn at a different time. It doesn't, for instance, affect commuters, or they can define that they want to post temporary speed limits, or they can close the road altogether. But that's to help them make decision based on the kind of burn you need to do. So in conclusion, we have developed this framework to simulate the condition typical of prescribed fire operation. We're doing validation. It's undergoing under a DoD-funded ESTCP project. We're actually going to go and validate this visibility piece soon. We really want to get to raw visibility because we feel like it's something that affects people and is not quite talked about much. And in the models we have, there are no prior assumption on how much smoke is lofting off the ground and how much is staying, like some of the other indexes that are commonly used in the community. And we do want to add in the effect of air moisture condensation on the visibility effects. So thank you for listening in.
This is amazing. I think the viewers of these lightning talks are used to me saying this by now, but I'm always blown away by the number of types of predictions that we can make by putting these models and types of data collection together, and the granularity with which some of those predictions can be made, thinking about different roads and their speed limits and just applying that sort of thought experiment to how long do you need in order to not end up in the trunk of the driver in front of you. I know what I'm about to ask is a question that would bear a lot of research and produce a complicated answer. So I'm just sort of looking for your intuition here. One of the things I pulled out of this talk is that a lot of these models, it appears like they're plausibly very sensitive to small changes in the inputs that get plugged into the model before you create the predictions. Do you have a sense of how much difference it makes to correctly predict the type of trees in the area, the height of the trees, the circumference of the trees, those sorts of questions, whether that has a big impact on what you're predicting downstream?
That's actually something we're working on right now, because we feel like we really need to understand the sensitivities to give confidence interval in what we predict. It's never going to be just one number, 23 minutes. That would be overly confident. We really want to go down the route right now. What we're doing is importing fast fuel inputs, for instance, as they come out of fast fuels. So statistically significant trees, but not in the right place.
Yeah.
Versus using an ALS-informed product. And so in this case, you fly above your forest, you know where every tree is, and then you put them down and on the land where they actually were. And you use also TLS, the terrestrial lidar, to do more of the sub-canopy type of information. So we want to see on those, what do you lose when you cannot afford to go out and image it before the burn? We really want to do that. And how much it means for the fireboats, how much it means 40 kilometers downwind. Do you really, does it really change? Is it really sensitive? Maybe yes, maybe no. And it will depend also on weather condition, because again, if you have like diurnal variations, you may see that the timing of the fire will influence where the smoke goes. So it may hit different communities differently. So I think this is actually a very important topic to get into and to assess.
Excellent. Well, thank you again for your time, Sara, joining us today. I'm sure that we all appreciate it. Those of you watching at home, please continue our series of lightning talks on wildfire and wildfire management technology. We will see you there.